could use those. Yeah, thank you for recording, Bruce. If you can use those, do you see my screen sharing? Do you see the book and the letter? Yeah, perfect. So don't hesitate to show yourself and start using those little answer. If you printed them, great. If you haven't, just take a piece of paper, take a large pen, and if you want to share your yourself, I can see you, and I think it's more fun this way. Just before, fantastic. I see some letters. Excellent, great, Mike. And Rowan, excellent. And Linda is looking for something. No, hiding. So if you want to show yourself, that I think that's more fun. Just a show of hand, who has the ARRL book and who's got the Gordon West book? So Gordon West first. Okay, very good, excellent. Yeah, I see Amanda, Megan. Good. And who's got the ARRL now? Show of hand. No one. Okay, so we all got that. The Gordon West. Very good. I'm going to start with just a very quick reminder on the basic. Most of this morning will be technical. So we're going to dive right in the technical, but before that, any question on what you've learned so far the last week and yesterday evening and this morning? Any question? Any kind of question on ham radio? If you do, just unmute yourself. If no question, let's go with the first equation. So the first equation is the wavelengths. So we put the letter lambda, and it's 300 divided by the frequency. And the frequency is in what unit? Anyone? You can unmute. What is the unit for frequency? Yeah, Jonathan, you wanted to say something? No one knows the unit of frequency. It's hertz. Capital H, small z. What's the unit for the wavelengths? It's a distance.
The meters.
It's meters, exactly. Okay, and that is, it's actually a velocity. So that's a speed equation. So 300 is actually 300 million meter per second. And that's the speed of light, 300 million meter per second. A speed equal a distance in meter divided by time. And here you have the invert of the time. So that's really is a speed equation if you think about it. Now, how do you use that for ham radio? Very simple. If you know the frequency, let's say the frequency is 148 million of hertz or megahertz. So you divide 300 by 148 or 150, that's about 2. So your wavelength is going to be 2 meters. Does that make sense? If your frequency is over 400, like let's say 440, 300 divided by 450 roughly, it's going to be a little less than a meter. So it's going to be about 70 centimeters. And really the 2 band you are going to use as ham radio with a radio like this one are the 2 meter and the 70 centimeter. So the 2 meter band, if you look at the frequency, it goes from 144 to 148 million of hertz. My bad here, I say hertz, I meant million of hertz, because otherwise I would have to do a 300 million on the top. 70 centimeter, anyone knows the frequency that you have access to? And it's if you don't ARRL, put a really nice document together. I'm going to try to make it in focus. Okay, so the 70 centimeter, you can see it's 420 to 450. The 2 meter band, 144 to 148. As a technician class amateur radio operator, you have access to all those bands. So everything in the VHF and UHF. In the HF, you have voice access only here on the 10 meter between the 28,300, so 28 millions of hertz to 28.5 megahertz. And you have access to the 15 meter, but only in CW. Anyone know what CW is?
Sorry, can you hear me?
Yes.
I think there's a mistake on the formula that you wrote on the previous. It should be in megahertz, yeah.
Yeah.
Okay.
Yeah, I made a mistake. You are correct. Thank you for that.
Yeah,
very good point.
Sorry, go ahead. I apologize.
No, perfect. No, that's great. So 420 million of hertz to 450 million of hertz. Okay.
If I start to interrupt also, can you briefly just describe what is the reasoning why these frequencies are described in meters? Is it making what's the? I assume it makes it easier for some reason.
Right. So it's just, again, it's a conversion because we know the speed of the radio wave is constant. It's the speed of light. So it's easy to convert from one to another because you just have a constant. It doesn't vary here. That 300 always stays 300. So you can either speak in megahertz, which is cycle per second. It's the invert of a time. It's in something per second. Or you can talk in distance. And it's interchangeable. There is no really, it depends what you're talking about. If you talk antenna, for the length of antenna, it's nice to discuss distance because then you can see that the length of this antenna. So the length of this antenna is going to be a fraction of this one. It's actually a quarter of that dimension here. That's about 19 centimeter. So it depends what you talk about. If you want to look into the frequency you use on the radio, you're going to use frequency. But again, you can go from one to the other. Typically, when we talk distance, we mentioned the band in distance. It kind of covers a large range of frequency. So when we said a 2 meter band, we really mean all those frequency. When we speak frequency, you usually spell out a very precise frequency, like, for example, 146.589. And so very precise frequency. Does that answer the question? Any other question on that? So just another quick reminder. So HF, high frequency. Then we have VHF. What VHF stand for? Very high frequency. UHF. What does UHF stand for?
Ultra high frequency.
Excellent. HF, start from how many megahertz to how many megahertz? I'll give you the answer. Again, million of hertz. Million of hertz. VHF goes from 30 million of hertz to 300 million-hertz. Okay, so that's the UHF. And UHF goes all the way to 3000 million-hertz or 3 gigahertz. It's the same thing. Does that make sense? If you look at the distance, 300 is easy because it's 300 divided by 300. So the distance is going to be 1 meter here. 300 divided by 30, that's 10 meter. 300 divided by 3, that's going to be 100 meter. And 300 divided by 3000, that is 0.1 meter or 10 centimeter. Okay, will that make sense? Any question on that? Okay, so that's kind of the reminder. That's the first equation. For the technician class, you need only 3 equations. That's the first one. And you're gonna use this one for anything to convert band to frequency. If you have to calculate antenna size, you're gonna use this equation. So it's useful in a lot of cases. All right. So next we are going to look at electronic, and the first thing we are looking at is you have a source of electricity. So let's put the source of electricity here. So that's your power source right there. And then to that power source, so a power source creates a force. We call it electromotive force. And that electromotive force is in what unit? It's in volt. Okay. Now to that, you can connect. You can connect any device here. So I'm gonna make a very simple one, just a simple resistor. And then I will put a device that measures the intensity of that electric current. So the intensity driven here, put the letter I, and the intensity is in what unit? It's in ampere. Okay, so electromotive force in volt, the current, the intensity of the current in ampere. Here is that little device measure the intensity. It's an amp meter. It measures intensity of the current. If I want to measure the voltage, what I do is I put my voltmeter connected here, and I'm going to connect it in parallel. So those two are in parallel, right? So if you want to measure a voltage, you measure in parallel. If you want to measure a current, you see those two are in series. They go one behind the other. This is 2 elements in series in one circuit. These two are in parallel in that same circuit, right? Does that make sense? So there are a number of questions on that. Any question you have regarding the volt, the amp, current, electromotive force? So there are 2 kinds of current. There is a direct current, so it flows only in one direction, and that's it. It just flows this way. That's called direct current. Direct current. And you have also what we call the alternative current. It's kind of the same as the direct, but it changes this direction. So sometimes it flows this way and sometimes it flows the other way. So One cycle, it goes, half of the cycle goes this way, the other half, it flows that way. And so if you look at the voltage, when you have an alternative current, function of time, so that's the voltage, and that's the time. If you have a direct current, it's a straight line. If you have an alternate current, it's a sinusoidal. It goes up and down and up and down. And so when it goes into the negative space, that's positive. When it goes to the negative space, that means it goes the other way, reverse way. Does that make sense? Very good. So what kind of electromotive force you're aware of? Obviously, the power plant, the big power plant, they make a lot of electricity, but also batteries, all kinds of battery create electromotive force. The battery generate a direct current. It's not alternating. The power plant, they have big machine that make alternating current. For the battery, one thing to remember is you can recharge a lot of different battery, but the ones that have are made with carbon do not recharge those batteries. Those are not rechargeable. So carbon burns don't recharge. Okay, let's go into the PowerPoint slide. I'm going to stop sharing for a second and start sharing again with the PowerPoint slide. Do you see my PowerPoint slide? And now will be your time to use the little card with the answer. So you see me, you see my face with the answer A, B, C. So this is a reminder. The frequency cycle per second is in hertz, electromotive force in volt, electrical current in amps, the resistance is in ohm, capacitance in farad, and I'll go through that in a little while. And that's what I just presented, a power source and a load. And yeah, different type of battery. So carbon, zinc, do not recharge those. Alternate current. Okay, first question.
Paul, oh, there it is. Never mind, sorry.
Yeah, go ahead with your question.
No, that wasn't a question. I just couldn't see the PowerPoint for a minute, but now it's up. Okay,
very good. Okay, so what is the electrical term for electromotive force that cause a flow of electrons? So yeah, A is the right answer. What is the unit of electromotive force? Yeah, A again. Which instrument would you use to measure electrical potential? B, I see B. Yeah, B is the correct answer. A voltmeter, electromotive force is in volt. What is the correct way to connect the voltmeter to a circuit? B, yes. In parallel with the circuit. Which of the following battery is rechargeable? It's kind of correct, but yeah, D is the correct answer. If you don't see carbon, you're good. They can all be charged. Okay, now I'm pretty sure you all know the right answer on this one. B, indeed. How much voltage does a mobile transceiver typically require? That's kind of a common sense. Yes, think of your car. What the battery, your car battery is a 12-volt battery. Where should the negative return connection of a mobile transceiver power cable be connected? Again, probably kind of a common sense. Exactly. the engine block is kind of acting as the return. What is the name of the flow of electron in the electric circuit? So yes, D is the right answer. It's the current. And so that is the intensity is in amp, and it's the current. Which instrument is used to measure electric current? So the force is in volt, the current is in amp, and you use an amp meter. Exactly. How is an amp meter usually connected to a circuit? In series, that is correct. A is correct. Electrical current is measured in which of the following unit? Again, the current, not the electromotive force. I see D. More answers. The A would be the force, the electromotive force. Here we're looking at the current. So D is indeed the right answer, yes. Which of the following is a good electrical conductor? Common knowledge. Yes, copper. What is the name of a current that reverses direction on a regular base? A, perfect. A is indeed correct. Why should wiring between the power source and radio be heavy gauge wire and kept as short as possible? Maybe a little bit of a common. Yeah, A is correct. What must be considered to determine the minimum current capacity needed for a transceiver power supply? So efficiency. Yeah, all the above. That is correct. D is correct. Which of the following device or circuit changes an alternating current into a varying direct current signal? So that would be changing the voltage if you answer A. What you do is you have an alternating current and you kind of make it straight. So you rectify it. Yeah, B is correct. Again, if you do the visual, that sine wave into a flat line, you rectify it. What is the name of for a current that flows only in one direction? That is correct. I see B. Correct. B is correct. Okay, let's go into the different component. I'm going to stop sharing for a second and go back to. So you see my the page here, the white page. Okay. And if you want to unmute, that's totally fine too. And if you have any question, okay. So different component now we have. We are going to see. So the first one is very simple. It is just a wire. So that is just a copper wire. And in that copper wire, what you have is you have an electrical current with an intensity I flowing through it. Okay. Then another component we have is a resistance. So the resistance kind of resists the flow of the electron. So the current is flowing in there, but there's a little bit of resistance. How do we measure the voltage across a resistor like that one? The voltage, we measure it in series or we measure it in parallel?
Parallel.
In parallel. And in series, we measure what? We measure the intensity or the current in amp. That's in series, right? Next component, it's a coil. So the coil, we kind of draw it like that to make it simple. Same thing, if you have a current. So that's basically a copper wire that you make a coil. You know, you have like a, it's simple device. If you have direct current, it will act just like that straight wire. When things change is when you have alternating current. When you have alternating current in that coil, what happens is you create a magnetic field inside the coil. That magnetic field will resist the flow of electron when they alternate. And the faster they alternate, the more you have resistance or impedance. The next component we have is a capacitor. So capacitor is basically two metal plates that are separated with a dielectric. Dielectric do not conduct electricity. So air, vacuum, plastic, glass is a dielectric. It's in between those two plates. If you have a direct current, that acts as a switch, an open switch. The current will stop here. And if you have a direct current, you're gonna accumulate all the electron. It's gonna get accumulated on that plate. And it'll push the electron on the other side. So you'll create positive charge on the other plate. And same thing, how do we measure voltage across a component like a capacitor? In parallel. So you can measure the voltage here. So if you have a direct current, I say it's an open circuit. And now if you have current alternating, what happens is those negative charge will move this way, and those positive charge become negative, and so it switch. And if you switch faster and faster and faster, if the faster you alternate, the less resistive it is. If you alternate very slowly, it's like a direct current, so you have an infinite resistance. The current is not going across. But if you alternate very, very fast, eventually that will appear as a straight copper line if the frequency is high enough. At very high frequency, there are almost no resistance. Okay, so we said resistance. And the unit is ohm. This is inductance or inductor. Sorry, missing the C. And the unit for an inductance is Henry. And this is a capacitor. And the unit for capacitor is farad. So the more ohm you have in the resistance, the more resistance. The more Henry you have in an inductor, the more inductance you have. And the more farad you have in the capacitor, the more capacitance you're gonna have. Those two components usually only really useful for alternate current. If you use direct current, they're not going to help anything because again, this is going to act like a straight line and this is going to act like an open circuit. But when they alternate, they impede the current of electricity. Any question on that? Okay. one more component. I'm going to put it on the side here. It's a diode. So a diode, if you have the intensity this way, this is an arrow, it goes through. But if you want to try alternating this way, it stops. It's not going to go through there, right? It stopped right here. That is kind of the stop line. So it goes only in one direction. It does not go the other direction. That is a diode. And for a diode, you have that is usually on the component. If you have the physical component, you have a little stripe that indicate the way the current is not flowing. That's the positive side. It's called the anode. The negative side, it's called the cathode. Okay. And again, it flows in only one direction. So if you have a direct current, it's not really useful. Now, if you have alternate current and you want to flow only in one direction, to rectify, for example, a diode is quite useful component. All right, let's dive into the PowerPoint presentation. I'm going to share the slides. Did you see my PowerPoint slide? Okay, very good. All right, so this is a diode with the anode and the cathode. And again, diode let the flow going on in one direction. This is a light emitting diode, a different type of diode. And when you see those little arrow going outside, that means it's light getting emitted. So LED, light emitting diode. Okay, what electronic component allows current to flow in only one direction? Is that A, C, C? Yeah, C is the correct answer. What are the name of two electrodes of a diode? Any answer on that? That is correct. I see C. Yep, C is correct. How is the cathode lead of a semiconductor diode usually identified? Yeah, it has a stripe. Resistor. The resistor, they resist the flow of current. And there are several sizes, and the unit is ohm. What electrical component is used to oppose the flow of current in a direct current circuit? That is correct, the resistor. That is a nice cartoon, I like it. So you have the electromotive force, it's pushing the electron. So the current is flowing, it's measured in amp. That's Mr. Amp. He's in trouble, Mr. Amp, because Mr. Ohm is giving him hard time. So, and ohm is the resistance, and the current is having a hard time. The higher the resistance, the more difficult for the current. Okay, oh, sorry, I went too fast. What instrument is used to measure resistance? Yeah, ohm meter, because the resistance is in ohm. Sorry, my computer is acting weird. What type of component is often used as an adjustable volume control? Sorry, I give you the answer. When I click once, it doesn't do, and then I click a second time and it goes too far. What electrical parameter is controlled by a potentiometer? It controlled the current, the resistance to current. A resistance, correct. Again, which of the following is a good electrical insulator? Yeah, common knowledge. Yeah. What type of electrical component stores energy in a magnetic field? Magnetic field is C is the right answer, is in inductor. In a capacitor, you have electric field, not magnetic. Okay, inductor, just a coil of conductor material, typically copper, aluminum, metal. You can have a variable inductor. And again, in that coil, you have the magnetic field that is getting stored, and a current creates a magnetic field. A magnetic field will induce a current, and in an inductor, it kind of opposes the current. So the spacing, the diameter, number of turn, all that affect the inductor. Again, the inductor is measured in Henry. Inductors are like resistance. They add when they are in series. So more inductor in series will create an overall higher inductor. If they are in parallel, think about a hose where you increase the size of the hose and it resists less. So if you put them in parallel, like the bottom graph, the equivalent inductor is lower than the smallest of the three or of the two. And that's kind of all you need to remember, because in the question you will see an answer. It's going to be either higher, a number of lower number, and if you know if it's in series, it's going to be obviously a higher number because you add them. If it's in parallel, it's going to be a lower number. And you don't need to remember any formula for that. So what electrical component is usually composed of a coil of wire? Inductor, correct. What is the ability to store energy in a magnetic field called? Yes, that is correct, inductance. What is the basic unit of inductance? The Henry is correct. What is meant by impedance? Yep, A is correct. It opposes the flow of current. What are the unit of impedance? So impedance kind of resists the flow of current. And the resistance is, yeah, in ohm. That is correct. Okay, capacitor, I mentioned 2 plate, conductive material, typically metal, separated with a non-conductive material. That's the symbol. 2 flat line also works. You can have a curved one. can have variable ones. Yeah, keep in mind that capacitor can store energy. There's an electric field into those two plates. And if you have a high electric field and there's nothing connected to it, it's going to stay. It's not going to go away. The magnetic field, on the other hand, in a coil is if nothing happened to it, it disappears. The electrical field is going to stay. And if you touch the two ends, you're going to discharge it, and you can feel it if it's a big capacitor. Okay, capacitor, again, the size of the plate dictate the size of the capacitor. So if you put them in parallel, the equivalent size is going to grow. So it's the opposite of the resistance and inductor. In parallel circuit, they add up. In series, the equivalent capacitance is going to be less than the lowest of the three or of the two. Okay, what is the ability to store energy in the electric field? Yep, I see D. That is correct. What is the basic unit of capacitance? And if more of us want to play, go for it. Don't be shy. It's fun. And again, there's no harm to give a wrong answer. Basic unit of capacitance is A is correct. Farad. What electrical component stores energy in the electric field? That is correct. B is the capacitor. What type of electrical component consists of two or more conductive surfaces separated by an insulator? Yep. I see the correct answer here. Any more answers? D is correct. I think I clicked. Oh yeah, I did click, and no, sorry, I give up the answer. What electrical component is used to connect or disconnect electrical circuit? This one is kind of a common knowledge. What electrical component is used to protect other circuit component from current overload? Common knowledge also. Yeah, I see A. Any other answer? That is correct. Okay, different kind of fuse. So let's see here. Yep. So the right size of the fuse is if the fuse is too small, it's going to blow constantly, and you will have to change it all the time. If the fuse is too big, it won't protect your circuitry because it will never blow. So you have to size it just right. So which of these components can be used as an electronic switch or amplifier? Okay, now is a time to maybe give you some more information. So let me stop sharing here. And start sharing there. Okay, so the most complex component we're gonna look into is the transistor. So a transistor is really, so it has 3 wires connected to it. So and there are 2 types of transistor, the bipolar and the field effect transistor. So for bipolar, you have like a N, P, N, so negative charge, positively doped, negatively doped. And you have the base, You have the collector, and you have the emitter. So that is a bipolar transistor. The little symbol for that one is something like that. And so you have the base here, emitter, collector, and you can put a little arrow going like that. So that's your component and the three connections here. So those are the advantage of a bipolar transistor is they are very, very fast. Unfortunately, they tend to be not so efficient and dissipate some heat. So great for high power and high speed, not so good if you pack millions or billions of them in a integrated circuit. For the integrated circuit, what we have is the field effect transistor. So field effect transistor has two metal, and I'm drawing that. So that's a metal, and it's the gate. That's one connection. That's actually a semiconductor. And so here you have the source. And here you have the drain. And in between, you have a dielectric. If you apply a voltage here, it creates an electrical field. And it will change that semiconductor into conducting or not conducting. And same here. If you applied a voltage here, you're going to change that semiconductor here into conducting or not conducting. So that's those two types of transistor. They kind of do the same function. This one advantage is very low power. It doesn't dissipate very much heat at all. Yeah, the little cartoon for this one is all right. So here you have the gate, the drain, the source, and you can put a little arrow there. So that's the symbol for this transistor. What they are used for? They're used for two things. They're used for logic, and so they either let the current pass or not pass. If it passes, it can be a 1. If it doesn't pass, it's a 0. So it creates 0, 1, 0, 1, 0, 0, 1, 1, 1 logic. So it's very useful for, again, integrated circuitry. All the logic into the component you have in your computer, cell phone, they are built with billions of those little guys like that. They are also used to amplify. So what happens is if you put a small signal here, and let's say a small little signal, it can be random. Time. And let's say this is millivolt, very small signal in here. So obviously it doesn't create any energy. The source is giving a very high voltage. Let's say the source is 10 volt, just for example. And here we have the 10 volt. And here we have 0.001 volt. So 1 millivolt, okay? So million times less. So here what you're gonna see is that will never go exceed the 10 volts. So that point will be the highest point. And so you're gonna have that. But what you see is this one is amplified. It acts as if you amplify that tiny little signal and make it much, much stronger in voltage. Does that make sense? Again, there's no magic. The source is giving the power. But here you put a very tiny little signal and you get a huge signal there. So that's called the amplification. And the gain is by how much you amplify. Okay, so in that very case, amplify maybe 10,000 times. Okay. Any question on that? Can you see?
Yes. Sorry, this is Rowan. I'm just not clear, and maybe it's not relevant. Which direction is the voltage entering from and exiting from?
Yeah, I don't think it really matters, but yeah, the source will drive. So basically, the electricity flows this way, and the base and the gate will control how much the drain or the collector gonna receive. Does that answer the question?
Yes.
And on the source, it can be a constant 10 volt. And on the collector, on the drain, it depends on what you apply to the gate. It can be anywhere from 0 to 10 volt in that very case, or from 0 to 1 volt if it's a 1 volt on the source. Does that make sense?
Yeah, thank you.
Okay, very good. Any other question on the transistor? I know it's a little more complex component. If no question, let's share the PowerPoint slides. Okay. Which of these components can be used as electronic switch or amplifier? Again, the switch does the 0 and the 1. That is correct, C. Okay, transistor. It's a semiconductor. It has a semiconductor that can either let the current flow through or stop the current, and it doesn't flow. So you can amplify, or you can just do on and off. Two kinds, bipolar or field effect. So bipolar transistor, field effect transistor. The bipolar emitter-based collector, if you like funny things to juggle your memory, you can use those. Field effect transistor are very common in the MOSFET metal oxide. In my little drawing, I showed you the metal, the oxide, and the semiconductor. So the MOSFET, metal oxide, semiconductor, field effect transistor, those are the most common. You have billions of them in your pocket, in your phone, everywhere around you. So that's the little symbol for the FET. Again, they obviously have 3 contacts, 3 connector. Unlike the other component, the resistor has only 2, capacitor has only 2, inductor has only 2, but the transistor has 3 connections. Okay, it has the field effect transistor has a source, gate, drain. Again, it's the same as the emitter-based collector. It's just they name it differently. Okay, what class of electronic component is capable of using a voltage or current signal to control current flow? Yep, I see a D. That is the correct answer. What is the term that describes a transistor ability to amplify a signal? Yeah, I see an A and another A. What are the 3 electrode and PNP or NPN in a transistor? Again, so that is for a bipolar. A bipolar is emitter, base, and collector. Yeah, it's memory. So yeah, it's the way people have been calling those. Oh, sorry, I give it away. Which of the following component can be made by 3-layer of semiconductor material? Yeah, definitely the transistor. What does the abbreviation FET stand for? A, that is correct. Okay, a little break. Let's do a time check here. So 10:15, and we are okay. Catching up a little bit. Any desire on how long we take the break? Is a 5-minute break good, or you want longer?
I'm okay with 5. This is wrong.
Okay, so let's meet at 10:20.
I'm gonna have to pop off for a bit. I'm getting called into work, but I will review the video. Thank you very much, Paul. Do appreciate it.
Very good. Thank you, Jonathan, and good luck with the test. If you have any question, don't hesitate to contact Bruce or me.
Absolutely. Yeah, I took a few practice tests last one on a ham study.
Okay.
But I will keep studying and I'll let you all know if I have any questions. Thank you.
Okay. Thank you, Jonathan. Good luck. Any question in the couple minutes we have? All right, let's resume. Can you see my my screen okay with the formula wavelength equal 300 divided by the frequency? Anyone can see that? Yeah, okay, very good. So that's, as I mentioned earlier, that's the first formula. So we have two new formula coming, and they are pretty simple formula, same type, multiplication, division, addition, subtraction. Those are all you need for the technician class. Next one is Ohm's law. So the electromotive force equal the intensity of the current time the resistance. And so that you can memorize it as ear, like your ear, you listen. It's one simple way to memorize it. The electromotive force, anyone can tell me what's the unit for that? Unmute yourself, and if you want to tell me. Anyone?
Volts.
Volt. The current intensity. The unit.
Amps.
That is correct. And the resistance. Anyone? Linda, I think you're saying something, but you're muted.
Oh.
Yeah. Ohm. Very good. That's the second equation. And so if you know two, you can easily calculate the third one. And I'll show you a quick, a very simple way to do that in a few slides. For the power, so now we have the power, it is equal the intensity of the current time the electromotive force. So I think we already know what the current intensity is. It's the same, it's in amp. And the electromotive force is in volt. We already know that. The power is in what? What unit?
Watts?
Yes. The unit is watt, Mr. Watt. And you can remember it as pi if you like eating cakes, pie. So ear and pi, those are the two formula. So now we have, with that, we have the three formula you need to memorize, and you're good for the technician class exam. This is it. There's no other formula you need to memorize. So one more thing before we dive into the question is the type of circuit. So parallel versus series. So a circuit in parallel, as I mentioned earlier, so that you have your source and you put all your component in parallel. So let's say a resistance, you can have a capacitor, you can have an inductor, you can have a voltmeter. All those are in parallel. In series, so you have your power supply, and then you put your first component here, you put a second component there, you put, let's say, ammeter here, and you put your inductor there. And here, if you want to put an ammeter, you can put it here. You can put it anywhere, but you're going to have different reading because the current's going to split here. the current is, there's only one path for the current. So the emitter will capture that. Any question on this? So here the voltage is the same for all the components. Here the voltage is going to be different for all the components. So you have a voltage 1 here, a voltage 2 there, a voltage 3. And the sum of all the voltage 1, 2, and 3 is the total voltage on the source plus voltage 4. The voltage gradually drops through in a series circuitry. In parallel, the voltage is constant. Now, if we look at what the current does, in a series, the current here, I, and I, and I, and I, is the same everywhere because it has no way around. It has to go through that. So it's the same current here and there and there and there and everywhere in that circuitry. Where here, it's different. So you have your current I here, but then it's going to split. One's going to go here, I1, and another current is going to go there, I2. Okay? So I1 plus I2 equal I. That is correct. And then it's going to split again. So you have I3 and I4 and so on and so forth. Okay? So in a parallel, when you have a point, you have 3 wires coming out of that point, 1 coming in, 2 going out. The current is going to be different. And the current I1 and I2, it depends on what you have after. All you know is the sum of those two equal this one. That's all you know. In series, the current is the same everywhere. In parallel, on the other hand, the voltage is the same everywhere. In series, the voltage is different everywhere. Does that make sense? Any question on that? I tried to give you a visual for what's coming, and when you see the question, if you kind of remember those visuals, series and parallel, it will greatly help you answer the question. Okay, let's start sharing and go to the slides. Okay. All right. So Ohm's law, again, remember here, electromotive force equal the current intensity times the resistance. One simple way is you can draw that little circle and put the E on top, and that bar means equal. So E equal I times R, and that vertical bar is the time. So that bar is either the equal or the divided. Okay, so E equal I times R. So you have this one. If you want to solve for E, you put your sum on the E, and the answer is I times R. If you want to solve for the I, all you do is you put your sum on the I, and the answer is E divided by R. And if you want to solve for the resistance, you put your sum on the R, and the answer is E divided by I. So what you can do is, for your test, you can quickly draw that ear circle, and you can draw the exactly same circle for the power, and it's the pi circle, where you have obviously the P, the I, and the E. Same technique. And here it is, the pi circle. If you want to use that, you are totally fine. You have a scrap paper for your test. You can first thing you can do is draw those two circles and write the first equation, and that may help answer some questions. So same idea, you put your sum on what you want to solve. Any question on that? Okay. All right, a visual for resistance drop in a circuit. So it's the effect of resistance and the voltage drop in the circuit. That's kind of the visual here. So you have a voltage there, and the resistance, and across that resistance, the voltage is dropping. Okay, so we have a number of questions that's going to look very much the same. It's just if you have a calculator, you can use it, or if you can calculate. It's simple math you can do in your head. So you have a 12-volt source, and the resistance is going to be 4 ohm or 3 ohm or 2 ohm. And so if you want to solve for the intensity, it's the electromotive force divided by the resistance. Okay, so those are the answer. Any question on that? Does that make sense? Again, so you have 12 volt. Okay, let's go to the question pool. Which term describes the rate at which electrical energy is used? That might be a tricky question. I didn't.
I'm going to say C.
Yeah, that is correct. It is the power. Oh, sorry, I give away the answer again. Sometime I click. Anyway, electrical power is measured in which of the following unit? So what? Let me see. Okay. What is the formula used to calculate electrical power in DC circuit? So all you need to remember is pi. Yep, I see A. A is correct. So how much power is being used in a circuit when the applied voltage is 13.8 volt and the current is 10 amp? So again, pi. I think you can do that math on your head. You can use the scrap paper or calculator if you want, but that's pretty simple math. So go ahead, and what is the answer? I see A. A is the correct answer. How much power is being used in a circuit when the applied voltage is 12 volt and the current is 2.5 amp? Again, we look at power, voltage, amp. So the formula is pi. And B is the correct answer. How many ampere are flowing in a circuit when the applied voltage is 12 volt and the load is 120 watts? That's weird. Yeah. Okay, so the formula here is pi. So we are solving for I. So what? Yeah, I see a B. That seems good. Yep, 2 B's. Perfect. B is the correct answer. Again, you you solve for the intensity. So you put your sum on the I, P divided by E. P is 120 watts. The voltage E is 12 volt. So 120 divided by 12. What formula is used to calculate voltage in a circuit? And that's the ER. Yeah, I see an A. Any other answer? A is correct. Very good. What is the voltage across a 2 ohm resistor if a current is 0.5 amp flowing through it? Again, we're going to use the ER formula. Yeah, I see a correct answer. Ah, I see a not correct one. Yeah, very good. A is the correct answer. Again, your ER formula, the E is what you're looking for. E equal I time R. Oh, do you see my mouse when I move around, or you don't see it? Yeah, okay, good. So what is the voltage across a 10 ohm resistor if your current is 1 amp? Again, the ER formula. Yeah, that is correct. B. What is the voltage across 10 ohm resistor if your current is 2 amp? Correct. D. In which type of circuit is voltage the same across all components? The voltage is the same across all components. So the picture is, yeah, I see B. What else? Any other answer? Yeah, B is correct. It's parallel. What is the voltage across each of 2 components in parallel with a voltage source? So in parallel, voltage is, yeah, I see a good answer, D. Again, in parallel, the voltage is the same everywhere, across all the components. I can show you the little picture after. What is the voltage across each of 2 components in series with a voltage source? So again, now we're in series, no longer in parallel. Yep, C is correct. What is the formula used to calculate current in a circuit? So it's the ER formula, but we solved for current. B is correct. What is the current flowing through a 24 ohm resistor connected across 240 volts? So what formula are you going to use? Pi, ER. Yep, that is correct. What is the current in a circuit with an applied voltage of 120 volt and a resistance of 80 ohms? More answers? Yeah. Correct. D is correct. 120 volt divided by 80 ohms. What is the current through a 100 ohm resistor connected to 200 volts? So we solve for I. We know R, we know E. That is correct, 2 amps. In which type of circuit is current the same through all components? So picture the circuit where the current is the same everywhere. Is it the series? Is it the parallel? Is it a resonant branch? Yes, series, you got it, very nice. What happens to current at the junction of 2 components in series? So you have your component in series, and in between the component, you have a junction. There's only 2 wires. So current, if you remember a series, every element is following one another. That's a series. And the current has only one way to go. Yeah, I see a good answer. Any more answer? Correct. It's unchanged. What happens to current at the junction of 2 components in parallel? Okay, so in parallel, you see the ladder. Yep, I see a correct answer. That is correct. A. It depends on the value of the components. What formula is used to calculate resistance in a circuit? More answers? So we're going to use, yep, that is correct. You got it. B is the correct answer. What is the resistance of a circuit in which a current of 3 amp flow through a resistor of 90 volts? Very good, 30 ohm. Which is the resistance in a circuit for which the applied voltage is 12 volt and the current flow is 1.5 amps. Yep. That is correct, 8 ohm. I think I clicked, but it's not moving. So I'm going to click again and give the answer away. Yeah, sorry about that. What is the resistance of a circuit that draws 4 amp from a 12 volt source? So you got the answer, but yep. All right. Finding the path of least resistance. Okay, so I think I kind of draw a few representation of component. So I think you might be able to go through that series of questions. So what is the name for standardized representation of component in an electrical wiring diagram? Yes, that is correct. It's schematic. What do the symbols on the electrical schematic represent? The electrical components, that is correct. Which of the following is actually accurately represented in electrical schematic? Yep, that is correct. The way they are interconnected. Okay, so there are a few questions with a little diagram like that, and they ask you the name of one of the components. So that is figure T3. What is component 3? Very good. You all got the right answer. Variable inductor. What is the component 4? I didn't give that, but maybe common. Yeah, very good. Kind of common knowledge. It's or by deduction, it's none of those, so it's got to be the antenna. Which of the following is combined with an inductor to make a tuned circuit? I didn't mention that. But we talk about inductor and what other component? And this is for alternative circuit. In alternative circuit, what component really makes a difference? You have the inductor and the capacitor. Yes. Yeah. Those two combine in a tuned circuit means at a certain frequency, it really resonates. What of the following is a resonant or tuned circuit? Again, those two components that really like alternative current. Yeah. Any other answer? Yeah, that is correct. Capacitor and inductor. Those are the components that are very useful in alternating current. Resistance, not so much. What is component 1 in figure 1? T1. Yep. Very good. A resistor. Component 2. Correct. Transistor. Component 2 in figure T1. Oh, what's the function? Yep, that is correct. It controls the flow of the current. What is component 3 in figure T1? I guess common knowledge, some guessing. Process of elimination. Yep. What is component 4 in figure T1? Not sure about that one. Component 4. It's remember the little diagram? I start with the electromotive force. Yes, correct. It's the battery. Does that make sense? It kind of looks like a capacitor because the capacitor can store energy, and the battery stores energy. But on a source battery, one line is longer than the other, where the capacitor, those two lines are like an equal sign.
So is the D the ground? The ground was what those other components were, the very end of that connection? Yeah,
the ground is at the bottom here, those little like fork thing that are symbol for the ground. Yes. Yeah. If you see my mouse, I'm circling the ground here. And see, here is the power source, and they put 2 bar equal distance. I don't like that. I prefer when the top one is longer, kind of like the other diagram. But yeah, that's a source of energy, electrical energy. Okay, for this one, what is component 3? I think common knowledge here. Yep. single pole, single throw, and there's only we don't look at double and combination of single and double. Component 4. So component 4 is this one. So think in your life, you have 2 coils and with metal, and they are kind of connected with a core, common core, 2 coils connected with a common core. And you usually use that to change voltage. Correct, it's a transformer. So you have one coil here, the other coil here, and that's the core. That kind of part of the transformer. Okay, figure 6. I think that one is easy. I know you know this one. Component 6. I see a good answer. Correct. It's the capacitor. Component 8. Okay, the giveaway are those little thing that are getting emitted here. Correct. A LED. Component 9. I think you will guess that one. You know it. That's correct. Absolutely. Variable resistor. What is the following display an electrical quantity as a numeric value? A meter. Correct. A meter. What is a relay? That is correct. I didn't mention that, but a relay is basically a switch that is controlled electrically, so you can remote control. What type of circuit controls the amount of voltage from a power supply? A regulator. What component is commonly used to change 120 volt AC to a lower AC voltage? We kind of discussed that. Yeah, I see good answer. Common knowledge here. Transformer, yeah, that is correct. What is the name of a device that combines several semiconductors and other components into a package? Common knowledge. I see a good answer. More answers? More guess? Yeah, very good. Integrated circuit. Okay, so let me stop sharing for a few minutes. And go through. Okay, so the decibel, how does that work? So basically, decibel is converting multiplication and division into addition and subtraction. So, and the only one you need to remember is +3 decibels. That is totally equivalent to multiply by 2. Okay. If you do a +10 decibel, that is very simple to remember. It's equivalent to multiply by 10. And we use that a lot. So if you want to do plus, if you want to multiply by 1,000, it's going to be plus 10 times 10 one time, plus 10 times 10 another time, and plus 10 times 10 another time. So time 10 times 10 times 10, that's time 1,000. Plus 10 plus 10 plus 10, that's plus 30. So plus 30 is going to be 1,000 times, right? If you want to do a billion, so a billion is 9 times the time 10, time 10, time 10, time 10, 9 times, right? So you have a number with 9 zeros. So that becomes a really, so 9 times here. 9 times plus 10, so plus 10, plus 10, plus 10, plus 10, that's plus 90. Plus 90, 90 is a small number. A billion is a massive big number. So that's where the power of decibel is coming handy. It's converting really big numbers and multiplication into small number addition and subtraction. And really, that's all you need to remember to answer all the questions. The only thing I'm adding here is the negative, so you kind of remember, but I'm pretty sure you're gonna guess. Anyone gonna guess what the negative 3 decibels is gonna convert?
Does that divide?
What was that?
It divides it.
Yeah, exactly. It divides by 2. And a negative 10 will do what? Divide by 10, exactly. Okay. So now if you want to do a 2 times 10, that's going to be how many decibel? That's times 20. A times 20 would be plus how many decibel?
Plus 6.
Um,
No, sorry, times
2 times 10. If you look here, and again, it's not in the test. It just so that you understand. So time 2 times 10, that's time 20. It's going to be plus 3 plus 10. That's plus 13, right? Again, not in the test, but just for the fun, so you understand how this works. In the test, you're going to see divided by 4. How do you divide by 4? You divide by 2 and divide by 2 again, right? So here's going to be negative 3 and negative 3 again, which is negative 6. Does that make sense? Good. Again, you convert with the decibel scale, you convert all kinds of complicated multiplication into simple addition and subtraction. That's what it is. Okay, let me go to the question. Oh, maybe another thing. I think, yeah, we'll go through that in the slides. All right. Okay, so decibel scale is using log, a logarithmic, which you don't need to know for the test, and it really converts big number with multiplication and division into smaller number with addition and subtraction. Positive means positive decibel means you multiply by something. Negative decibel means you divide by something. Okay, and that's all you need to remember for the test. Plus 3 decibel is roughly time 2. It's not exactly time 2, but it's very, very close to time 2. Negative 6 decibel is very, very close to divide by 4. And plus 10 decibel is very, very close. It's exactly time 10. Okay, if you want to answer that first question, what is the approximate amount of change measured in decibel if the power increased from 5 watts to 10 watts, so that's a time 2, and the time 2 is roughly equivalent to how many decibels? So if you remember the slide I just showed, I'm gonna stop for a second. Stop sharing. And share again. Here we are. So again, a time 2 is a +3 decibel. It's kind of it's really painful, because if it was +2, it would be so much easier, right? The thing is, it's a log scale, and the definition is here. That's the definition for the decimal. The decibel scale is +10 decibel is time 10. That is an approximative. It's an approximative time 2, an approximative divided by 2, but it's close enough. Or it's an approximative +3 and approximative -3. Okay, so all you remember is time 2 is roughly +3, time 10 is exactly +10 decibel. Okay, let's stop that and share again. Okay, now going from 5 watt to 10 watt. Yeah, any other answers? That is correct, +3 decibel. So approximate amount of change measured in decibel when the power decreases from 12 watt to 3 watt. So you divide by 4, right? So divide by 2, divide by 2. That is correct answer. Any other answer? That would be -3 decibel would be divided by 2. But here we go from 12 to 3, so we don't divide by 2. It's not 6 watt, here's 3 watts. So we divide by 4. So we do a -3 and another -3, which is a negative, correct, a -6. What is the amount of change measured in decibel of a power increase from 20 watt to 200 watts? So we multiply by how much here? Exactly 10. So time 10 is, yep, I see a right answer here. More answers? Yep, A. That's the easy one, is time 10 is +10 decibel. It's the way that the decibel scale has been defined. So it's an exact. Oh, sorry, I clicked twice. What does the abbreviation LED stand for? I think we've seen that. Which of the following is commonly used as a visual indicator? Yep, LED. Okay, so here is a lot of a kind of multiplier name. So the one that are really useful for radio and for the test is the kilo multiply by 1,000. So kilo something means 1,000 something. So kilogram means, you can unmute yourself. If you can all unmute yourself. And a kilogram means how many grams?
1,000.
Exactly, a kilogram is 1,000 grams. Mega is a million. So a megawatt is how many watt?
A million.
Million.
A million watt. A megahertz is how many hertz?
A million.
A million hertz, exactly. Giga we use very little in the exam test pool, but giga is a billion. So a giga byte would be how many bytes?
Billion.
A billion. That's very common in the computer world. Now, if we go, and tera, I don't think we use for this test. If we go small, deci and centimeter is a hundredth of a meter. So a millimeter would be what fraction of a meter?
Thousandth.
A thousandth. A milliwatt would be what fraction of a watt?
1,000.
Exactly. So if you have 1,000 milliwatt, that's how many watt?
A watt.
1 watt, exactly. I think the micro, nano, and pico is very rarely used in the test. I think the pico is used once. So if you have that question, if you have good memory, great. Otherwise, bad luck. But the other one, they're gonna come quite often. So I would suggest you focus your memory on mega, meaning time a million. So now just a fun one. A kilo tomato is how many tomatoes?
1,000.
1,000.
Exactly. Oh, you're good. Because very many people say, oh, it's maybe 5 or 6 depending on the weight. 5 or 6 tomato would be a kilogram of tomato, right? So very good. So you got it. You got that scale perfect. So I'm not going to spend too much more time on that. And let's dive into the question. Oh, sorry, we were there. Okay, what is another way to specify a radio signal frequency of 1,500,000 hertz? I see a good answer and a bad answer. Yeah, a good answer is still up. Correct. It is A. It's kilo means 1,000. So if you take that number times 1,000, you have 1,500,000. What if the frequency display show a reading of 2,425 millions of hertz? What frequency is that in gigahertz? Yep. Yes, indeed. Very good. 2.425 gigahertz. How many volt are equal to 1 kilovolt? Very good. That one is easy. Excellent. Good job. If an ammeter calibrated in ampere is used to measure 3,000 milliampere current, what reading would it show? Yeah, I see correct answer. 2 correct answer. 3 correct answer. Excellent. 3 amps. Very good. Which of the following frequency is equal to 28,400 kilohertz? So again, you have a kilo here. So you have another 30 there, really, in hertz. Yep. I see a good answer. Anyone else? Yep, 2 good answer. Not sure about that one. Again, this is 28,000 kilohertz, so it cannot be 28 kilohertz. All right, giving it, it's A. It's 28 million of hertz. Again, the kilo here, if you eliminate that K, you put 30 there, it's 28 millions. Which of the following is equal to 500 milliwatts? Yep. Yeah, I see one. Yeah, very good. All good answers. Half a watt. Because 5,000 milliwatt would be 5 watt, but here we have 500. How many milliamperes is 1.5 amperes? Yeah, very good. 2 good answers. More answers? Yes, very good. How many microfarad are equal to 1 million picofarad? That's the unlucky question if you get it. But if you know your unit is B, is 1 microfarad. If you maybe you'll remember it's 1 microfarad if you take the time the test soon enough. I think I clicked and it's not moving. I'm afraid I'm gonna give away the next one. Yeah. How many volt are equal to 1 microvolt? I think you knew that one anyways. It's 1 millionth of a volt, micro. Okay, oh, sorry. Which of the following type of solder is best for radio and electronic use? The answer is rosin core solder. It makes a very nice, smooth looking solder and nice, good contact. Okay, let me try. Okay, what is the characteristic appearance of a cold solder joint? So cold solder is usually not what you want. So it's not going to be nice and smooth. It's going to be grainy and dull. Exactly. C is the right answer. And you want to avoid that. You want the bright and shiny. Okay, multimeter, it measures voltage, it measures current. So voltage is in volt, current is in amps, and resistance is in ohms, right? Those are fairly inexpensive, good to have in the house. If you do a little bit of do it yourself, you probably have one. It's again, you have cheap meter for $15–20 and they work quite well actually. And for if you want a fancy one, you can spend $50 or $70 and you have a fancy one. Like this one. That Fluke is probably it's a little more than $20, but it might hit the $100 at most. They're not very expensive. Oh, sorry. Again, my mouse is double clicking. Which of the following measurements are commonly made using a multimeter? Yeah, voltage and resistance. Let me see if I can do a better job not clicking twice. Oh, sorry about that. Here we go. Okay, which of the following precautions should be taken when measuring circuit resistance with an ohm meter? Yep, that's a good answer. Ensure the circuit is not power. When you put your multimeter with an ohm, the multimeter is gonna put a little bit of voltage. If you have a powered circuit, it's gonna damage your voltmeter. Well, okay. Which of the following might damage your multimeter? I think we just discussed that one. What was the answer? Sorry, I didn't watch. Yep, that is correct answer. Anyone else? attempting to measure voltage when your setting is resistance. What is probably happening when an ohmmeter connected across N-power circuit initially indicates a low resistance and then shows increasing resistance with time? So something is changing in your circuitry, and what component can discharge? Yes, indeed. What component can store energy is the capacitor. Yep. Okay. Let's see how we're doing on time. 11:15, and the antenna should be okay. So I don't know. So let's continue. So I think I'm doing okay on time here. All right. So antenna. What is an antenna? So that, all right. So that is an antenna, and a few things to know about antenna, how that works. So if you remember one of the formula here, we have the if you have a wave, electromagnetic wave, so with an electrical field and a magnetic field combined together, making electromagnetic wave, and that wave travels very, very fast at 300 million meters per second. And so if the frequency is slow, you need a really, really long antenna. And that's why we have very high frequency in the millions of hertz. So that's very fast, means millions of cycles per second, extremely fast. And still, if you are with 300 millions of cycles per second, 300 divided by 300 is 1. So 1 meter, basically a yard. That's still a fairly long size antenna. So how antenna works is basically the electrical current goes up, and ideally what you want is it to go down. When it reaches the tip of the antenna, you want the electrical current to go down. So what you want is to match that frequency here with the length of your antenna. So if you have a given frequency, let's say 300, so you want that length to be, so the current actually in that antenna is going this way, going down, going on the other side, going back here. So the full cycle is going to be 1, 2, 3, and back to the original. So that length is actually a quarter of the wavelength on the size of the antenna. For an antenna like that. For a dipole antenna, and I'll show you a dipole antenna in a few minutes, you have the whole antenna. I'll show you that in a few minutes. Another thing to keep in mind is the electrical field is parallel to the antenna. So again, the electricity is going up and down. So the electrical field is getting between that point and that point. So it's in that direction, the electrical field. The radiation is going broadside. So it radiates on the side here. There is zero radiation here. There's zero radiation there. All the electromagnetic wave is going broadside in all directions. So it goes this way, it goes towards me in all direction. So if you wish, perpendicular, if the plane of the wave is the plane of that sheet of paper, if you wish. That's how it works. Now antenna, they have a gain. So this antenna has a very low gain, but typically a dipole has a gain of slightly more than 2 decibel. So not quite 2x. Again, 3 decibel is double. 2 decibel is not quite double, but it's good to have a little bit of gain with a dipole. If you want a higher gain antenna, what happened is you have to compromise somewhere. So high gain antenna, like a little Yagi, here, I don't know if you can see that little Yagi. That's a Yagi antenna. It's kind of big for the video, but you see the top. That's called the directing element or director. This one that has a little plastic thing, that's the element that radiates. So that's the radiator, the active element. And that is actually a full dipole. So the electrical current is going to go this way, this way, and that way. So again, 1, 2, 3, 4. And those 4 little elements makes the full wavelength. So that's a quarter wave. That from that side to that side is half of the wavelengths. Okay. So dipole is half wavelengths. So you have the director element, which is gonna, again, the electromagnetic wave is broadside of this. So it's gonna go this way, that way, not too far that way, because what we have here is called a reflector. So it's gonna reflect and go back. So this one directs on the top, this one on the back, here, this one on the back reflects. So the wave is going to be going this way. And because you reflect, as I mentioned, a regular dipole is almost a ×2, because everything that goes this way is going to be reflected. You're going to multiply again a couple of times. So you're going to have almost a ×4 gain with an antenna like that, which is a 6 decibel. Because you have a director, you can increase that gain a little more. What happened is it makes it narrower in direction. So it's going to really direct all the electromagnetic wave in this direction. What is an electromagnetic wave? What is that physically? Anyone, if you want to unmute yourself? Any physical sense, something that makes sense to people? Because radio wave is kind of an abstract thing. It's light. Radio wave or just light, they are not visible light, but they're light. They have all the property of light. It's an electromagnetic wave. It travels at the speed of light. It reflects on reflecting surface. It diffracts. It has everything, all the property of light, and its energy is proportional to the frequency. So it's just not visible light, but it's light, and that is something I think interesting to remember, because when you have radio, you have reflection sometimes. So if you have that little radio, your signal again go broadside, but it may reflect on the building and or on a hill or on a mountain, just like light get reflected. Any question on the antenna? Last little concept on the antenna is this light is polarized. So the radio frequency is a polarized electromagnetic wave. And the polarization, again, is dictated by the electrical field on the electromagnetic part. And it's parallel to the direction of the antenna. So if I have this radio like that, the polarization is in this direction. It's not that direction, but this way. Okay. I think we are ready to go to the question. Let's go to the question pool here. Right. Okay, so antenna. So it transmits a radio wave in vacuum, in air, very well. In solid, not so well. So this is a dipole with one side going this way, the other side going this way, and this is just the connection, the cable that connects the dipole to the radio. The radio is going to be connected there. And again, the dipole, the total length is half the wavelength. So that's another antenna. So it looks like a dipole, and the radiation is broadside on the antenna. That elevation pattern, I think I can skip. There's not much question on that but it's something that comes really handy to understand when you do general and extra. Okay. Yagi is an antenna that is called a directional antenna. It has an increased gain because it drives all the radio wave into one preferred direction. So it has a reflector and it has driven elements, sometimes one, like the antenna I show you, sometimes many. Sometimes there are 2, 3, 4, 10, 20 directing element. And you have only one driven element. It's like a dipole. Sorry, I confused you. The driven element is the one that's connected to the radio. The reflector and the director are not really connected to the radio, but they really drive the radio signal. So that's a Yagi. So the driven element here, again, connected, that cable goes to your radio. The reflector reflects all the signal in this direction. And you can have multiple director. And the more director you have, the higher the gain, but also the less coverage you have. So you have to point your antenna in the very, very specific direction. If you point it slightly off, you won't hear anything and nobody will hear you. But if you're pointed in the perfect direction, you can use very low power with a Yagi antenna. Again, there's no power created by the antenna. The power is only directed in particular direction. So 3-element Yagi, again, one driven element, and the driven element is usually right next to the reflector. And then you have a lot of directing element. On this one, the driven element is here, the reflector is right there, and all those are directors. Okay, let's go to the question pool. Which of the following describe a simple dipole mounted so the conductor is parallel to the Earth's surface? So again, the dipole, yeah, it's horizontally polarized. In which direction is the radiation strongest from a half-wave dipole antenna in free space? If you remember, the radio frequency go, yes, exactly, broadside to the antenna. What is approximate length in inch of a 6 meter half wavelength dipole antenna? Again, a dipole is usually half wave. So here you have 6 meter, half wave means 3 meter. So all you need to do is convert the 3 meter in inches. And a meter is about 39 inches, I believe. So if you have 3 meters, yep, I see a good answer. So you just need to convert the 3 meter in inches, and that's 112 inches. How would you change a dipole antenna to make it resonant at a higher frequency? So remember the formula. Wavelength is 300 divided by frequency. So it's the invert. Yes, exactly. So if you want higher frequency, you don't make the antenna longer, you make it shorter, because it's the formula goes by the invert. What is the approximate length in inch of a quarter wavelength vertical antenna for 146? So the approach to that is, remember the formula, 300 divided by the frequency. So 300 divided by 146, roughly 2, right? 300 divided by 150, so about 2. So 2 is the wavelength. But now you have a quarter wave. So it's not 2 meter, it's a quarter to meter, which is half a meter. And half a meter is how many inches? It's about 19 inches. Yeah. Does that make sense? So what type of antenna are the quad, the Yagi, and the dish? So read the answer. There's one that, yep, correct answer. Yes, they're all directional antennas. What is a beam antenna? Beam meaning kind of focusing in one direction. Yeah, I guess I give the answer away here. Yeah, the beam is kind of like a laser beam. It really focuses the energy into one direction. When using a directional antenna, how might your station be able to access a distant repeater if building or obstruction are blocking direct line of sight path? Yep, absolutely. Find a good reflection, a nice building, building with the, so metal sheet reflect, and building with the window that have those metal coating are very good reflectors. Which of the following method is used to locate source of noise interference or jamming? Yep, good answer here. And how do you do that? You take like a Yagi antenna, a directional antenna, and you do radio direction finding. Absolutely. Which of these items would be useful for a hidden transmitter hunt? Yep, I see a good answer. More answers? Yep, very good. Directional antenna. What is the gain of an antenna? Again, you're not adding power magically. All you do is take that power and direct it into a specific direction. And when you do that, the gain increase, so the power in that direction looks like it's amplified. But really what you did is the power that was to go everywhere, you focus into one direction, and so you have more energy going to that direction. But the total energy of the radio is not increased. It's kind of like using a magnifier, and you have the sun, the light of the sun, and you take your big magnifier and you focus all that sunlight into one point. A directional antenna is doing precisely that. So the answer is correct. What antenna polarization is normally used for long distance weak signal CW single sideband contact using very high frequency, ultra high frequency band? So that is a tricky question. Normally is vertical, but for single sideband, and the key is weak signal long distance, we use horizontal. So you know, everything else is vertical. So it's a trick question here. What can happen if the antenna at opposite end of a VHF UHF line of sight radio link are not using the same polarization? I think that's kind of a common sense. If you think of it, yep, exactly. It would significantly weaken the signal. So if you have two radios at 90-degree angle, basically only 1% get transmit from one antenna to the other. If they are, as opposed to if they were parallel. If they were parallel, 100% of the signal would transmit. If they are perpendicular, only 1%. What is an advantage of using a properly mounted 5/8 wavelength antenna for VHF or UHF mobile service? Yep. A is correct. It improves a little bit. And again, detail is going to general and extra class. Which of the following describes a type of antenna loading? So in antenna loading is you do something electrically to the antenna, so its length looks different than its physical dimension. So you have the physical dimension of the antenna, but what really matters is the electrical appeared dimension. So if you can make a short antenna appear electrically longer by using a capacitor or inductor. So if you add those components into the antenna, electrically they look shorter or longer, even though physically they are in the same dimension. So that's how you make some antenna fairly small where they electrically are looking like they're much bigger. So the answer is, yeah, correct, A. If you insert an inductor, electrically, you change the electrical appeared dimension. Feed line. All right, so feed line are not the people waiting at a fast food chain. They are the cable that connect the radio and the antenna. And let me show you a few. Let me do a time check here. 11:40. Okay, so what we are planning on doing now is a lunch break. So how long you want your lunch break? I think in the agenda it says about 40 minutes. Looks like I'm a few minutes early, which is great. So when would you like to come back? Is like 12:30 a good time? I see a thumbs up, 2 thumbs up, 3 thumbs up. Okay. Looks like anyone object to 12:30? Okay, we all come back at 12:30.